All right, let's talk about a number that, for the longest time, everyone thought was, well, impossible. I mean, they literally called it imaginary. But here's the crazy part. What if I told you that this so-called imaginary number is actually essential for the electricity that's powering your screen right this second? Yeah, let's dive in. So, it all kicks off with this one simple question. And if you've taken an algebra class, this probably feels like a total trick question, right? You know the drill. 5 times 5 is 25, and -5 times -5, that's also positive 25. So how on earth could you ever multiply a number by itself and end up with a -1?
And you know what? For centuries, the answer was just, you can't. That was it. Within the world of real numbers, that number line you learned about in school, this problem was basically considered unsolvable. There was just no number on that line that would give you a negative when you squared it. End of story. Or so they thought. But here's where it gets really cool. Mathematicians, they're a creative bunch. Instead of just throwing their hands up and saying, no solution, they decided to, well, invent one. They literally defined a brand new number just to solve this one nagging problem. And in doing that, they blew the doors open to a whole new dimension of math.
And here it is. Meet the imaginary unit, usually written as the letter I. The definition is super simple. I is the square root of -1. That's it. Now, you can't measure I on a ruler, but that's okay. Think of it as a perfectly legitimate mathematical building block, just as real and useful as the number 1. Okay, and this right here, this is the single most important consequence of that definition. Seriously, if I is the square root of -1, what happens when you square it? You just get -1. This one little identity, I squared equals -1, is the absolute key to everything else we're going to do. If you only remember one thing from all this, make it this one.
So this gives us a really powerful and honestly super simple rule for dealing with any negative square root. The formal math might look a little fancy, but the process is dead simple. Just think of it this way. You see a negative inside a square root, you just pull it out front as an I, and then you solve whatever's left over. Let me show you what I mean. Now, before we jump into some examples, check out this fascinating pattern. You might think that as you take I to higher and higher powers, things would get super complicated, right? But they don't. It actually repeats in this really clean 4-step cycle. I, -1, -I, and then back to 1. This predictability is awesome because it makes even huge powers of I surprisingly easy to figure out. Okay, enough theory. The best way to really get a feel for meh is to actually use it. So let's walk through a few examples together. We'll start basic and then work our way up a little, just to see how these rules work in the real world. So first step, a pretty straightforward one. How do we simplify the square root of -25? Well, based on what we just talked about, that little negative sign inside the square root is our big clue.
And here's how we tackle it. We can think of this as the square root of -1 times the square root of 25. We know the square root of -1 is just I, right? And the square root of 25 is, of course, 5. So we just stick them together. The answer is 5i. Simple as that. All right, let's kick it up a tiny notch. How about the square root of -12? Now this one's a little more interesting because, well, 12 isn't a perfect square like 25 was. So we're going to have one extra little step here. But that first step, it's always the same. We see the negative inside, so we pull it out as an I. That leaves us with I times the square root of 12. Now, we just simplify the square root of 12 like we normally would. We look for the biggest perfect square that divides into it, and that's 4. The square root of 4 is 2, so that comes outside the radical, leaving the 3 inside. And there's our final answer, 2i times the square root of 3. Okay, one more. Let's look at this one. It's got a bit of a twist. Notice there's a negative sign inside the radical, but also one on the outside. This is a classic spot where people get tripped up, but it's actually really easy if you just take it one step at a time. So here's the key. That negative on the outside, just leave it alone. It's just hanging out. The negative on the inside, that's the one that becomes our I. So we get -I times the square root of 72. Now we just simplify the radical. 72 is 36 times 2. And hey, 36 is a perfect square. The square root of 36 is 6. So our final fully simplified answer is -6i times the square root of 2. You know, whenever you learn a new concept in math, there are always a few common traps people fall into. So let's go over the biggest ones really quick, just so you know what to watch out for when you're doing these on your own. Okay, this one right here is by far the biggest and most common mistake. It is so tempting to just look at that and say, oh, -2 times -18, that's positive 36. But you absolutely cannot do that.
The rule is you have to deal with the negatives, pull out the i's first. When you do it the right way, you end up with an I squared, which we know is -1, giving you a totally different answer, -6.
And here are 2 other quick traps. First, it sounds silly, but don't forget to actually write the I. The square root of -9 is 3i, not just 3. It's an easy mistake to make. And second, always remember that I isn't just some random variable like x. It's a specific number with a specific value, the square root of -1. So at this point, you might be thinking, okay, this is a neat math trick, but why does any of this actually matter? It's got the word imaginary in its name, right? Well, the truth is, this number is absolutely fundamental to how the real world works, especially when you get into physics and engineering. Let me show you.
Think about the power coming out of the outlets in your wall right now. That's alternating current, or AC. And it doesn't just flow in one direction. It flows in waves, cycling back and forth, back and forth. And it just so happens that that cyclical 4-step pattern of I we saw earlier, it is the perfect mathematical tool for describing that exact wave-like behavior. And this isn't just some cute coincidence. Electrical engineers use these numbers. Fun fact, they often call it J instead of I so it doesn't get mixed up with the symbol for current. They use them every single day. It is absolutely essential for calculating things like voltage and designing the circuits and basically everything, from your phone to the entire national power grid. The math just flat out would not work without them.
So think about it. This whole amazing journey into a new kind of math started just because some people dared to create a solution for a problem that everyone else said was unsolvable. It really makes you wonder, doesn't it? What other problems out there that seem completely impossible today are just waiting for someone to imagine a new kind of number to solve them?